Imagine, imagine trying to find a specific book in a library that has literally billions of books.
Oh, wow.
Right.
Right.
But here's the catch. All the titles are written in a language you completely don't speak, and the books are organized entirely by, like, how they smell.
That sounds like a complete nightmare.
It is. It's an impossible task.
Right.
But that impossible task is essentially what we are asking computers to do every single time, we upload a photo or ask an AI chatbot a really complex question, or even just scroll through a feed of those hyper-personalized recommendations.
Yeah, the stuff we just take for granted every day.
Exactly. You interact with artificial intelligence all the time, but today our mission is to sort of pull back the curtain on the unsung architecture that's making that seemingly impossible task happen in, like, milliseconds. We are taking a deep dive into vector databases.
It's honestly the engine room of the modern AI boom.
Yeah.
And it's the part that nobody really sees.
Right, because it's hidden.
Exactly. I mean, everyone is so captivated by the flashy front-end stuff.
Right.
The algorithms that can suddenly write Python code or generate those crazy photorealistic art pieces or synthesize human voices perfectly.
Yeah, the magic tricks.
Right, the magic tricks. But the reality is, none of those models can actually function at an enterprise scale without a fundamental ground-up reimagining of how we store and search data.
Which is why we have this massive stack of technical architecture breakdowns, white papers, and engineering articles in front of us today. Our goal is to extract the really critical insights from all these sources.
Good luck to us, right? It's a pretty dense material.
It is dense, but we're going to decode the jargon, bypass all that information overload, and give you, the listener, a really clear, high-energy understanding of how these systems actually work under the hood. Because, honestly, these databases are rapidly replacing traditional data structures for AI tasks.
They absolutely are.
So understanding the mechanics here is basically, it's like getting the cheat code to the next decade of software development.
I agree with that. And, to even begin understanding the database itself, we have to look at the completely alien type of data that it's actually built to hold.
Okay, lay it on me.
Well, we're basically leaving behind the familiar world of words and pixels and audio waves, and we're entering this landscape of pure, high-dimensional mathematics. The source materials all center around one foundational concept, which is embeddings.
Okay, let's unpack this, because usually when we picture a database, we just picture a giant, really well-organized spreadsheet, right?
Right, the classic rows and column.
Exactly. There are columns, there are rows, you've got text strings, you've got integers, but the literature makes it very clear that vector databases handle dense numerical representations. They call them high-dimensional vectors.
Yeah, that's the technical term.
So how does a piece of the real world, like a picture or a word, actually become one of these vectors?
Well, think about the core limitation of a machine learning model, right?
Yep.
Like a natural language processing transformer or an image recognition neural network. It doesn't inherently comprehend human concepts. It has no idea what a dog is, it doesn't know what a sarcastic tone sounds like, and it certainly doesn't know what a sunset looks like.
It's just a machine.
Exactly.
Yeah.
So to process our world, it has to translate our inputs into its native language, which is math. So when you feed text or an image or an audio clip into a machine learning model, it runs that input through its neural network, and it outputs a massive array of numbers.
And that array is the embedding.
That array is the embedding, yes.
So if I'm getting this, the model kind of acts as a universal translator.
That's a really good way to put it.
Because instead of trying to teach a computer the actual definition of the English word apple, or like feeding it the exact RGB pixel values of a digital photograph of an apple.
Which is how we used to do it.
Right. Instead of that, the machine learning model translates both the word and the image into these massive numerical strings. And because the system natively understands those numbers, it suddenly processes both text and visuals on the exact same playing field.
Yes. And the depth of that translation is what makes it so unbelievably powerful.
Yeah.
Because we aren't talking about a simple cipher here where, A equals 1 and B equals 2.
Right, it's not a secret decoder ring.
No, not at all. These vectors are, as the papers say, high-dimensional. So if you imagine a physical room, it has 3 dimensions.
Right.
Length, width, and height.
Sure, X, Y, and Z axis.
Exactly. And you can pinpoint any physical object in that room using just those 3 coordinates. But these AI models, they map concepts across hundreds or sometimes even thousands of dimensions.
Thousands. I can't even visualize that.
You really can't visualize it in your head. But mathematically, every single one of those dimensions represents a distinct subtle feature or characteristic of the data being analyzed.
So it's capturing the essence of the thing mathematically. Like if it translates the word apple, maybe one dimension represents its fruitness, another is its color spectrum, and maybe another is its association with a certain multi-trillion-dollar tech company.
Exactly. The model generates this dense numerical representation that plots the exact location of that concept in a 1,000-dimensional mathematical space.
Okay, so we've mapped all these messy human concepts into this insane mathematical space. But practically speaking, if a user types the word puppy into a search bar, how does the system actually locate those coordinates without checking every single point in the digital universe?
Right, because traditional database search is absolutely not built for high-dimensional geometry.
No, I imagine it isn't.
Traditional databases fail here because they rely on exact matching, typically using SQL. In that classic paradigm, you demand a perfect one-to-one match.
Like finding a specific record.
Right. You tell the system to find the exact characters DOG in a specific column. So if the database holds the word hound or canine or puppy,
It just returns 0 results.
exactly,
Yeah.
0. The characters don't align, so to the SQL database, those records are totally irrelevant.
It's completely binary. It either matches perfectly or it just doesn't exist.
Yeah. And because of that extreme rigidity, vector databases basically throw SQL exact matching out the window entirely. Instead, they enable what the sources call semantic similarity,
Semantic similarity.
Yeah.
Okay.
meaning they search by meaning and context. Since the machine learning model translated both puppy and dog into high-dimensional vectors based on their conceptual traits like they are both pets, they're both animals, both canines,
Right.
their numerical arrays are mathematically similar. So in that 1,000-dimensional space we talked about, they are plotted right next to each other, forming a sort of conceptual constellation.
Okay, that makes intuitive sense. But how does the database actually measure that closeness? Like, how does it mathematically prove to the computer that puppy is closer to dog than it is to, say, a fire hydrant?
So the engineering papers we reviewed point to two primary mathematical metrics used to calculate this. There's Euclidean distance and cosine similarity.
Okay, Euclidean distance and cosine similarity.
Yeah, Euclidean distance is pretty straightforward. It's essentially taking a ruler and measuring the straight line physical distance between 2 points in that high-dimensional space.
Just a straight line from A to B.
Exactly. But cosine similarity takes a different approach.
Mm-hmm.
Rather than measuring the physical distance between the points, it measures the angle between the vectors, originating from a central point.
Okay, wait, let me make sure I'm wrapping my head around this difference, because reading about angles and magnitudes in the white papers, it can get abstract really quickly.
It definitely can.
So let's say I have a 5-word tweet about a puppy, just super short.
Okay.
And I also have a massive 500-page veterinary textbook entirely about puppies.
Right.
If I use Euclidean distance, the ruler method, it might say those two things are very far apart just because of their sheer size difference, the magnitude, right?
Yes, exactly. The textbook vector is massive compared to the tweet vector.
But if I use cosine similarity, it looks at the angle and realizes, hey, despite the massive size difference, these two vectors are pointing in the exact same topical direction. They're both about puppies.
That captures the dynamic perfectly. That's
Yeah.
exactly it. And that's why cosine similarity is incredibly popular for text analysis. It cares about the direction of the meaning, neutralizing all that noise created by document length.
That's brilliant.
It really is.
Yeah.
This shift from exact keyword matching to mathematical similarity metrics is the fundamental breakthrough. It's what allows AI to understand intent. It understands what you mean, not just what you typed.
Now, finding the closest mathematical coordinate makes total sense if you have, like, 1,000 items. But the sources point out that modern AI applications, we're talking global recommendation engines or massive corporate knowledge bases, they're dealing with billions of vectors.
Glowins, yeah.
So if I search for a movie on a streaming app, the system calculating the exact distance between my query and every single one of those billions of vectors seems computationally impossible. Like, I don't want to wait 5 minutes on a loading screen just to get a movie suggestion.
You wouldn't, right.
Yeah.
But you've hit on the major bottleneck. It's often referred to in the literature as the exhaustive search problem.
The exhaustive search problem.
Right. Comparing a query against every single vector is known as k-nearest neighbors, or KNN. And in a database of billions, KNN is incredibly slow and wildly expensive.
So how do they fix it?
Well, this brings us into the actual engine room of the vector database. It's the technical workflow of indexing. To make this functional for real-world applications, vector databases implement a 3-step workflow.
Okay, what are the 3 steps?
First, they embed the data up front. Second, they index that data for fast lookup. And third, they query and retrieve.
Well, step 2 is clearly where the heavy lifting happens, right? The indexing. How do you index a billion mathematical coordinates to find the closest match instantly?
So they utilize a whole class of algorithms known as approximate nearest neighbor search, or AN.
ANN. Okay.
And the key word there is approximate.
So it's not perfect.
Right. Instead of guaranteeing the mathematically perfect closest point by exhaustively checking everything,
Yeah.
ANN trades a minuscule fraction of accuracy for a massive exponential leap in speed. It finds the K closest matches, say, the top 10 or 50 vectors out of billions in single-digit milliseconds.
It's incredibly fast.
Yeah.
And the sources mention a veritable alphabet soup of algorithms powering this ANN approach. I saw HNSW, IVF, PQ.
Yeah, engineers love their acronyms.
They really do.
Yeah.
Let's break those down, though, because they seem to be the secret sauce here. Let's start with HNSW, which stands for Hierarchical Navigable Small World.
That is a mouthful.
It is. But think of an exhaustive search, like trying to find a specific book in a massive library by walking down every single aisle and reading the spine of every single book.
Which would take forever.
Right. But HNSW changes the game completely. It builds a multi-layered graph. It's like walking into that giant library, and instead of looking at the books on the ground floor, you go up to the top floor where there are only broad category signs.
Right, the highest level.
Yeah. You find the science sign, you take the stairs down to the next floor, which narrows it to just physics, you go down again, straight to the right aisle, and finally to the closest shelf.
You just skip all the irrelevant stuff.
Exactly. You didn't read every spine. Now, maybe you missed a book that was technically 1 millimeter closer to your perfect match, but you found the right section in 3 seconds instead of 3 years.
That multi-layered navigation is exactly how HNSW operates. It uses nodes and edges to quickly drop down into the densest neighborhood of relevant vectors.
And what about the other ones? IVF.
So IVF, or Inverted File Index, takes a clustering approach. It uses machine learning to group similar vectors into defined buckets ahead of time.
Like pre-sorting them.
Exactly. So when you submit a query, the system identifies the single bucket your query most likely belongs to, and it only searches inside that specific bucket, ignoring the rest of the database entirely.
That's super efficient. And then there's PQ, which is product quantization. This one really fascinated me because it's all about compression.
Yes, compression is vital here.
Like if you take a massive 4K Ultra HD photograph and you compress it into a low-res JPEG, you lose all those microscopic details, right? But the file loads instantly and you can still immediately tell it's a picture of a dog.
Exactly, and PQ does that to the vectors themselves.
So it shrinks the math.
Yeah, it splits these massive high-dimensional arrays into smaller chunks, compresses them, and stores a much lighter representation. So by combining these indexing algorithms, they often use HNSW alongside PQ, actually, the vector database achieves that crucial balance.
Speed and accuracy.
Right. It navigates the high-dimensional space with terrifying speed. It keeps memory costs manageable while still delivering highly relevant semantic matches.
Okay, I'm going to stop you right there, though.
Oh,
Because here's where it gets really interesting, and I want to push back on the architecture itself for a second.
okay, go for it.
Everything we've talked about so far, HNSW, clustering, quantization, these are brilliant search algorithms. But why is the tech industry building entirely new database companies just for this? Like, why are we calling it a vector database?
I see where you're going.
Why can't I just take an open source algorithmic index, like Facebook's FATIS library, and just bolt it onto my existing tech stack to run the math?
That is exactly the multi-million-dollar question in enterprise architecture right now.
Because it seems like overkill to buy a whole new database.
It does, but there is a massive distinction between a simple vector index like FaceI and a fully fledged vector database. An index is just a search mechanism.
Okay.
It's the engine, but it's not the car. A true vector database wraps that search engine in critical data management features, and the absolute most important being full CRD support.
CR create, read, update, and delete.
Exactly.
But wait, CRU is like databases 101. Every standard relational database since the 1980s has CRU operations. Why is this suddenly being touted as a massive selling point just because vectors are involved? Why can't I just update my index?
Because of the complex math we just spent the last 10 minutes discussing.
Oh, right.
Think about it. In a standard SQL database, adding a new row or deleting an old one is computationally trivial. You just pop it in. But in a vector index, All those vectors are intricately mapped in that multi-layered HNSW graph, or they're clustered in specific IVF buckets.
So everything is interconnected.
Highly interconnected. If you use a standalone index and you want to ingest a live stream of new data or delete obsolete vectors, you often have to recompute and rebuild the entire mathematical index from scratch.
Oh, wow. Didn't think about that.
Yeah, and that can take hours or even days for billions of vectors. A true vector database is engineered specifically to allow continuous streaming of new data, updating existing vectors, and deleting outdated information on the fly without ever shutting down or rebuilding the system.
Ah, I see. So the standard databases handle CRU'd fine, but they can't do the complex vector math. And the standalone vector indexes handle the math brilliantly, but they basically break down when you try to update them dynamically.
You nailed it. The vector database bridges that gap.
Okay, that makes a lot of sense. And the sources also highlight another crucial feature of a full database, which is hybrid search.
Yes, hybrid search is massive.
Because vector databases don't just store the mathematical arrays, right? They store those vectors alongside traditional metadata. So IDs, timestamps, categories, access levels, all that normal database stuff.
Right. And hybrid search is where this technology becomes truly indispensable for enterprise applications. It allows you to combine the semantic similarity of the vector search with the rigid keyword filtering of a traditional database.
So without the CRU-DOC operations and the metadata filtering, an AI wouldn't be able to process a practical prompt. Like, say I ask it, find me images that look conceptually similar to this specific photograph, but only show me results uploaded by user XYZ in the last 48 hours.
You'd be totally stuck. If you just had an index, you could find the similar images, sure, but you couldn't filter by the date or the user.
It wouldn't know what 48 hours means.
Exactly. A vector database executes that query by first filtering out all the metadata that doesn't match the last 48 hours criteria. And then it runs the ultra-fast semantic ANN search only on the remaining valid vectors.
Oh, that's smart.
It marries the precision and control of traditional data structures with the contextual, nuanced understanding of artificial intelligence.
And from an infrastructure standpoint, building a full database system brings scalability too. We are talking about horizontal scaling, fault tolerance, and serverless architectures.
Critical for big tech.
Meaning, if an AI application suddenly goes viral and you jump from 10,000 users to 10 million users overnight, a true vector database can seamlessly distribute that massive query load across multiple servers without the whole system just crashing and burning.
Because you cannot run a global, real-time business on a fragile index that has to be taken offline every time a user deletes their account. You need enterprise-grade resilience.
Okay, so let's ground all this theory in reality. We've covered the mathematical translation, the shift away from SQL, the crazy speed of indexing algorithms, and why you need a full database architecture.
It's a lot.
It is a lot. But where are you, the listener, actually experiencing this tech today? The sources outline a wide array of use cases. Image and video similarity is a huge one.
Oh, definitely.
Like when you upload a picture of a chair to a shopping app to find similar furniture you can buy. That's a vector database comparing the numerical embedding of your photo against a massive inventory of embeddings.
Yep. And recommendation engines heavily rely on this infrastructure as well. When a streaming platform curates a perfectly vibe-matched playlist for you, it has mapped your previous listening habits into a vector, and it's using approximate nearest neighbor search to find the closest matching audio content in milliseconds.
It's all math.
It's all math. But we really have to look at what is arguably driving the massive explosion in vector database adoption right now. And that's retrieval augmented generation, or RAG.
RAG. Yes, RAG is the buzzword of the year. Walk us through how a vector database specifically enables it, and more importantly, why it's even necessary.
So large language models, the foundational models powering all these modern chatbots, they have a notoriously dangerous flaw, which is hallucination.
Yes, they lie confidently.
Very confidently. They fabricate facts, they quote fake court cases, they invent statistics. And this happens because LLMs are ultimately just predictive text engines, right? They predict the next most statistically likely word based on their training data. They don't actually have a reliable factual memory.
Right, they don't know anything.
Exactly. So RAG is the architecture designed to solve this by grounding the LLM in external reality.
Wait, so when I ask a chatbot a question and it gives me an instant, highly accurate answer from like a 500-page corporate manual, It isn't actually reading the PDF in real time.
Not at all.
Hmm.
Months ago, the company took that manual, chopped it up into small paragraph-sized chunks, ran those chunks through an embedding model, and stored the resulting vectors in a vector database.
Okay.
When you type your question into the chatbot, your prompt is instantly embedded into a vector. The vector database then performs a semantic similarity search to find the specific chunks of the manual that are mathematically closest in context to your question.
That completely changes how I view these loading screens. So the database retrieves those highly relevant document chunks and basically injects them into the prompt behind the scenes.
Yes.
It tells the LLM, hey, answer the user's question, but strictly base your answer on this factual text I've just handed you.
Exactly. It
Huh.
effectively provides the LLM with an open book test, which prevents hallucinations and ensures the AI is citing accurate proprietary information.
That is so cool. Now, to facilitate this massive shift, the enterprise ecosystem seems to be fragmenting into a few distinct approaches. The sources specifically name-drop cloud-native solutions like Pinecone, Weaviate, and Milvus.
Yes, those are the big players.
These are purpose-built from the ground up to handle high-dimensional vectors. Like, a company might choose Pinecone because it's a fully managed serverless solution. They don't have to worry about the underlying infrastructure at all.
Right, it's plug and play. But the traditional database heavyweights aren't just sitting this out either.
Oh.
The architecture breakdowns highlight tools like pgvector, which is an extension that allows Postgres, which is one of the most popular relational databases in the world, to store and search vectors alongside standard data.
So for an enterprise that already has petabytes of data sitting securely in Postgres, adding an extension is often much easier than migrating everything to a brand new specialized vector vendor.
Oh, for sure. Much less friction. And major cloud providers like AWS and Google Cloud are also deeply integrating these vector search capabilities directly into their existing ecosystems.
So the market is really deciding whether it's better to add vector search to traditional databases or build new databases specifically optimized for vector.
Yeah, that's the current battleground. But honestly, regardless of the vendor, the underlying reliance on embeddings and semantic search is becoming the foundational layer for all intelligent software.
Okay, let's do a quick recap of the journey we've just taken. We started by looking at how machine learning models translate the messy, subjective reality of words, images, and concepts into embeddings, these dense numerical arrays floating in high-dimensional space.
Right.
We explored how this completely bypasses the rigid binary rules of SQL, allowing for semantic similarity searches that actually understand intent based on the mathematical distance between concepts.
Yeah, and we broke down the incredible speed of indexing, showing how approximate nearest neighbor algorithms like HNSW and PQ navigate billions of vectors by trading a little bit of absolute precision for massive speed.
And then we tackled why this needs to be a fully fledged database, complete with real-time updates and hybrid search to marry semantic understanding with traditional metadata filtering.
Which ultimately powers enterprise applications like RAG and dynamic recommendation engines.
It really is a fundamentally different way for computers to perceive and organize reality. But I want to leave you, the listener, with a forward-looking thought to mull over, building directly on a specific use case mentioned in our sources.
Oh, what's that?
Well, the materials list fraud detection and recommendation engines as key applications, but think about the broader implications of that capability. Vector databases are essentially mapping the semantic similarity of absolutely everything, including user behavior, microinteractions, spending habits, and anomalies.
Yeah, that's true.
What happens when human decision-making itself is perfectly embedded? As these systems continuously ingest and query billions of vectors in real time, mapping the mathematical coordinates of our daily habits and intents, how close are we to a digital ecosystem that doesn't just recommend what you want to see, but actually calculates and mathematically predicts your next action before you even consciously realize you're going to take it?
Wow, that's a profound paradigm shift. We are no longer just organizing information, we are organizing human intent.
Something to keep in mind the next time an application seems to read your mind. Thank you for joining us on this deep dive into the architecture of AI. Keep questioning the algorithms, and we will see you next time.